So back around the holidays, we had my friend Tom Mand stop in for a WiLLcast. What'd you think?
What a guy. He was so interesting. I mean,
Kind of does it all.
He does. The whole biochemistry thing, obviously not my background in the slightest. Didn't know a lot about it, but he is so passionate about what he does, and he did such a nice job explaining it, and there's a lot of excitement there, and that's always cool.
Yeah, I'm glad it came together. He had shot me a text when he was back visiting family, and got a tour of Wisconsin Lighting Lab, and then, I think a couple days later, I'm like, man, he'd be a great guest. So we kind of...
I think it was like a couple hours later. I don't even think it was a couple days.
So we came in on the Friday when everything was shut down and hammered out a WiLLcast, and I'm really glad we did it.
Boy, was it fun. It was, it's sneaky, though, when you do it on a day like that, because we could have talked to him for hours.
Yeah.
And there's no sense of time once you sit down and start chatting, especially when no one's in the building.
And it's cool. Like, he still, he knows his Wisconsin roots and, credits, working in his dad's construction company with kind of the hands-on approach to what he does. And what I really liked is he's in biomanufacturing. It's interesting to think about engineering and manufacturing at different scales. I mean, you can design and make a huge building. You can make, medium-sized products like we have, but they're making products at the microscopic scale, and just seeing the parallels of their process versus us versus, other companies is neat.
Yeah, the prototyping, the adjusting, the evolving, everything like that. And I mean, and it's also for a diaper.
Yeah.
Which everyone will hear about pretty quick here, but I personally have some skin in that game, so I'm all for it.
Yeah, it's a lot of technology goes into everyday products that you may not think about.
Yeah, and even talking about his hobbies, beekeeping, he got into a little bit, and that was so interesting, but there's so many parallels in that, and it's funny how all of his interests align, but, that's everything. Like you're saying, the manufacturing aligns what we do with what he does, which are totally on paper different things. Yeah. You see those similarities. So, yeah, it's always fun to make those connections.
Yeah, and understanding kind of the business and startup and science culture in the Bay Area where him and his wife and his son live, and some of the differences, some of the similarities, and yeah, I think you guys will enjoy this one. So enjoy this WiLLcast with my friend Tom Mand.
Up to here. I hear from the podcast I listen to like a fist away.
Yeah.
Well, Adam,
kiss the mic.
Adam's
that was the old.
Closer than that, so he'll be competing.
First started playing the band, somebody said kiss the mic, and I took that to heart.
I'm not much better.
Are you guys still playing quite a bit?
So there's Tyler and I play. There's two engineers on our software and controls team that are musicians. So company parties and things we'll play, nice. But not as much as we would like. And it's kind of like exercising, that every time you play, you're not in shape. Yeah. And then by the time you have the show and you're back in shape, and then it's like, I need to keep playing so my fingers stay in shape. But
is there like finger strength or just the calluses?
It's actually both. It's speed. I mean, the calluses, that's kind of step one, and then once you have the calluses, getting your speed back. But I actually have been playing some drums recently.
Oh, really?
So I bought a electronic drum set, something I can play with headphones on when the kids are in bed, and you actually get calluses from drumming too, which I never realized, but it's fun.
Cool. Did we talk about archery when I was here before? I've gotten into archery recently.
Are you serious?
Yeah, I'm starting to get like calluses on my hands. And,
recurve?
Yep,
or okay.
Recurve.
What? So where do you shoot?
There's an indoor range actually like right down the road from where I work.
Oh, that's cool.
And yeah, so they have 20 yards is the furthest distance they go, and it's actually kind of a interesting-ish story. We my wife's mother is like prepper light. She likes to think about.
That's such a way of putting it.
Yeah.
Prepper light. I love that.
I'm like prepper medium.
I'm not going to engage in this portion of the
I didn't realize
conversation.
I was going to go this direction, but I like it.
Yeah. So last holiday season, she got us a gift certificate for an archery lesson.
Oh, that's really cool.
We went to it, and it was a lot of fun. And I thought, maybe someday it would be great to get into this sort of thing. And then a couple months later, Naomi has some coworkers that have their own bows, and they like to go shoot at this outdoor range not far from our house. And so we went along, and I was like, okay, I think I'm going to do this. I know people that are into it. They have their own equipment, and it was a lot of fun. And that outdoor course, or that outdoor range, has a course that's like a golf course, but with targets. And so you walk along, you're shooting from different angles, different
Is
elevations.
it timed at all? Did they do a
So
speed round?
I don't know any details about it other than I really want to try this course at some point, but I feel like I need to work up to it. So I've only been doing it a couple months.
Have you heard of the ledge games?
I participated
wait.
5-6 years ago.
Okay.
Yeah.
Yeah, you'll have to come and give
could
some
be a ringer.
Yeah, some archery lessons. But with a recurve, you draw and then you drop down in one motion, or do you have an anchor point that
I anchor on my cheek.
On your cheek.
Yeah.
Okay.
That's sort of something I'm still figuring out, but
Yeah.
it's on the wall in the range I go to. It's like a 12-step process, and it's all about, for accuracy, doing the exact same thing the exact same way every single time. And so from stepping up to the line to the release, there's like things you're paying attention to. And I'm starting out with bare bow recurve, which is no sights, no counterweights, or like, if you see the Olympic archers, they have those like big stabilizer poles and things. I'm trying to avoid that for now because I want to be able to pick up a recurve and look down the tip of the arrow and line it up and shoot that way. And so that's what I'm working on.
What's the weight of your bow?
My draw is just 24 pounds right now, but I mean, holding 24 pounds for, let's say 10 seconds while you're lining it up, and then doing that 20 times more than 20 times, 45 times in a row in a round, the last few rounds I'm like shaking. So
are you actually, when you say look down the arrow, the arrow's not pointed at your anchor point or your target? Or is the arrow pointed at the bullseye?
So this is something that's a little bit interesting, actually, and I've only just started trying this, but recurve archers that have a sight, they a lot of times are drawing under their chin, and they're looking through their sight and lining that up, and you can sort of click it in depending on the distance from the target, because the arrow is parabolic, right? It's going to curve, and so the closer you are, the
higher in the target it's
going
to hit.
Yeah. And so there's like a classic thing where you shoot over the top of the target because
I've done that a few times.
Yeah.
I'm just taking notes, and maybe I won't score 0 at ledge games next year.
But if you don't have a sight, you are sort of stuck with either kind of aiming below the target, or what I've started doing is called string walking, where you have the arrow set in your nock, or your nock pin, whatever you call that part on the string, and then you sort of walk your fingers down beneath that nock depending on how far away you are. And on my tab that I hold the string with, it's like a little piece of leather. There's little etched marks in it. And so I sort of, at 20 yards, I know that I need to go down five notches, and I hold 5 notches below my nock and release it there. At 20 yards, I'm like 10 notches down, so I'm actually like maybe this far below my nock. And that allows me to put the point on the target and aim that way.
You have to snap your fingers? Or
They talk about sort of when you get to almost a full draw, and you line it up, and then you sort of do this it's like back tension. You squeeze your shoulder blades together, and as you're doing that, you're releasing, and then they say your like hand should kind of fling past. Maybe you like brush your neck or something like that. So these are all things that I'm working on. I can talk about
I've definitely seen that. Now that
some of the better archers.
Randy.
Yeah, my dad's pretty good. But
your whole family isn't I'm not gonna use the word annoying. Like they're annoyingly good at archery.
I'm probably the worst. Allie's pretty good.
Allie's a ringer. That's how she wins ledge games. I swear.
Ben is really good.
Yeah, Adam, you are though.
Well, maybe I'll be better now.
You're the
Tom's
best
given us
racer in the family.
Yeah.
You gotta take what you can get, man.
So archery and then beekeeping. So you're nice enough to bring us in some of your honey. How'd you get into beekeeping?
So I've always been into biology, nature, things like that. I've thought bees are just a cool little insect. And then when I was working in Knoxville, Tennessee at Oak Ridge National Lab, I came across a flyer that said, come check out our bee club's annual beginners beekeeping introductory course or class or meeting or whatever. And at the time, my wife and I were long distance. She was finishing her graduate degree in Illinois. I was in Tennessee, and I was like, nothing else to do. I'll go check this out. And I thought it was really cool. And I thought, maybe I'll try to get into it. I'll attend the monthly meetings for a while, maybe a year, just to kind of see what a year in beekeeping is like, and then maybe I'll get into it. That was in, I think, November. And then that spring, by the way, this is spring of 2020, I won a raffle at their club meeting, and that included a hive box, a veil, kind of the gear you need to get started. So I was like, well, I guess I got to find some bees now.
No time like the pandemic.
Exactly. So, I had an interest in it, had started thinking about it seriously before the pandemic, and then the pandemic hit, and I'm at home all day for months, and I got bees, and that allowed me to like get deep into it and really learn a lot about beekeeping and bees and kind of everything that goes along with it. And I've been doing it since then. I actually, when Naomi and I drove from Tennessee to where we live now in the Bay Area in California, we were in a U-Haul, pulling my car behind on a trailer with a hive of bees in the back of the U-Haul. So, because it's a pretty decent investment, several $100s in hive equipment and bees and all that stuff. And, I didn't want to just give them away and sort of give out something that I'd worked on for, months and months at that time. So I wanted to bring them with.
I'm just having the scene from Tommy. Is it Tommy Boy?
Oh, yeah.
That's all I'm thinking is the bees.
Yeah.
Sorry, obviously that didn't happen, but that's what
Right.
I'm picturing. Like, what's the risk of traveling with bees? I'm like, that would be it.
Yeah, it was definitely an experience. We stopped 2-3 times on the way there overnight, and we'd park at the hotel, and I'd be out there kind of checking the bees, and people are walking around, and I'm always like, nothing to see here. But yeah.
And you were saying that your hive has gotten better and better each year, and you select certain bees for certain characteristics.
Yeah. So there's this is sort of the biologist in me. Bees are really interesting in the way their genetics system is really interesting. So with humans, you think mom, dad, baby is like maybe 50-50 in between. But bees are different. So you have the queen bee is female. All of the worker bees you see are female. And then there are male bees called drones, and their only role in life is to mate with queens. They're like super specialized to mate with queens. They have enormous eyes to find queens. And so when there's a new queen, a virgin queen emerges from a hive, she'll leave and go out and mate. Maybe a handful of times she'll leave the hive to go mate with dozens and dozens of drones. And so she wants a large amount of genetic diversity. And that's what allows them to overcome any challenges they might encounter out in nature. Disease is a big thing. There are pretty significant parasites that are devastating beekeeping. And I feel like I'm getting off topic here,
this
but
is
great.
So there's something called the varroa mite. This is a mite that, if you thought about a similarly sized parasite to humans relatively, it would be like a frisbee-sized mite that sort of attaches onto us and sucks stuff out of our liver. That's essentially what's going on with the varroa mite. And there are different traits that honeybees have sort of evolved to allow them to adapt to the varroa mite. And so I'm not going to get into all of those details, but essentially there are people in the U.S. that are adamant about you have to treat to allow your bees to survive. They can use fairly harsh treatments. There are things called acaricides that are like some chemicals that you put in there that specifically will kill the mites and not the bees. But the thing is, the mites develop resistance to those sorts of things. There are concerns about those types of chemicals getting into honey. There's like all sorts of things with that. There are people who have some natural treatments, things like organic acids, oxalic acid. That's something that you can find in spinach. Foods that you naturally eat have high levels of oxalic acid, and that's one of the gentler treatments that people use. And And something that I'm trying to do is let the bees take care of it themselves. So I essentially try to be treatment free. There's a whole segment of beekeepers that are treatment free. And essentially what you're doing is selecting your colonies that deal well with the mites. That means that for me, at least, if I have a colony that makes it through winter, they're strong, they're healthy, they have a really great pattern of, laying eggs and brood, and they're making lots of honey, things like that, they're good to go. And I try to only select that queen and propagate her genetics.
Can you see the mite? Or
you can,
but you just look at the productivity and the overall health of the hive.
Yeah, so
how to select.
There are ways that you can measure the mite load in your colony. So the way that I do it is you take a certain amount of bees, you scoop them up, dump them into a jar with it's like a Dawn dish soap and water, or some people use like ethanol or something like that. And you shake them around. Unfortunately, it's usually around 300 bees. They all die. They're the sacrifice to make sure the rest of their sisters are okay. And you just, the mites will kind of release from the bee in that and fall to the bottom, and you count the number of mites. There are a couple other ways. Some people use powdered sugar, but there's like concerns about it not being as accurate because you really have to shake them. And people do that because they don't want to kill the bees. When you shake them with powdered sugar, you can put them back in the hive. But I still think like you're putting 300 bees into a jar and dousing them with powdered sugar, and you're shaking them up. And then I'm like, that just seems like torture. I'd rather just like, end it quick with the soap wash. And then, bees go through a high level of attrition anyways. A queen bee is laying, I forget the number, like 2,000 eggs a day. So that means that there are 2,000 bees a day, in a steady state that are dying.
Yep.
And those are the forager bees that are going out and gathering nectar and pollen and things and coming back. But eventually those are the oldest bees that are foraging, and they'll die out in the field. They'll either just drop dead, or a bird gets them, or whatever happens to them. And so 300 of that to kind of check the level of mites to me is like, I hate doing it. It needs to be done, and by the number, it's not that big of a deal.
And what is honey to the bee?
Honey is nectar. So they're one of the few. Like, I think there's only a handful of insects that live in large colonies that have stores to get them through winter or hard times, things like that. And so what they do is the foragers go out, they're getting nectar, they're getting pollen, they're getting water, they're getting sap to make like, it's called propolis, that seals up the gaps in their hive. They also think that some of the natural acids and things like that in sap can help give them some antiviral things. Anyway, for the honey itself, they are going out and getting nectar and bringing it back to the hive. They evaporate it. There's some enzymatic process as they sort of eat it and then kind of spit it back out and pass it from bee to bee. And that sort of converts nectar from flowers into honey. Honey is super concentrated sugar. It's so concentrated that nothing can grow in it. So you may have heard this fact that honey is the only food that is does not need preserving, that never goes bad. And it's because it's so concentrated that literally bacteria, fungus, things like that can't grow in it because they can't access the sugars. It's too like dry for them. In science words, the water activity is really low.
So you're saying before they have to hydrate it to consume it.
Yeah, exactly. So that I mentioned one of the things that foragers are going out to get is water. They use water to rehydrate that honey so that they can actually consume it. They have a few different stomachs. One is their honey gut, and so they can take honey into their stomach and then transport it. But then to actually consume it for the carbohydrates, they'll have to dilute it so that they can eat it.
So it's really, we're going to talk about your company and current role, which is like it's a biomanufacturing company, but this seems like biomanufacturing
Totally. Yeah.
as well.
Yeah. We haven't even talked about wax. Like
It's a byproduct of.
I mean, they make it.
They make it. Okay.
They have a specific. I don't know a ton of the wax details, but they have a specific gland that makes wax, and they form it into honeycomb, and they make bridge comb to kind of get from one area to another in the hive, and that to me is such a remarkable.
It's like they're scaffolding.
Yeah.
These are so much smarter than humans. Oh my god.
Yeah, and it's like
it's wild.
Yeah, nature has selected for this incredible insect that has all these incredible superpowers. So
you're here a few days ago. You and your family are back home for the holidays, and we're talking about your current company, your current role, and it was one of those moments where I'm like, man, I really wish we could do a podcast on this, just because it's fascinating. And in our business, we're manufacturing things. We're taking mechanical parts, electronics, a variety of inputs, but you guys are really manufacturing at the biology level,
right?
And I guess what Zymochem?
Indeed, yep, Zymochem. Yep.
So what do you guys do?
Yeah, we're a biomanufacturing company. We are basically trying to develop microbes and processes to replace materials that are traditionally made with petroleum with bio-based materials. The big project that I work on is a superabsorbent polymer. So superabsorbent polymers are in things like diapers. It's what allows a diaper to hold liquids. We call them insults in the diaper industry, I guess. These are polymers that, depending on what the liquid is, could hold hundreds of times their weight in liquid or in moisture. When we're talking about urine, we usually use like a 0.9% saline solution. That's just salt water. As like a mimic of urine, and we can hold our best material now in a metric we call free swell capacity. Can hold about 60 times its weight in water. So we're putting 10 to 15 grams of our SAP in a diaper, and it can hold whatever that math is, 300 plus grams of urine or whatever in the diaper. So what we're trying to do is replace the superabsorbent polymer that's already in diapers. That's made out of polyacrylic acid. It's petroleum based. It is made from oil, and it goes into a landfill and doesn't degrade for hundreds of years. I think the number I heard a few years ago was about 8% of landfill waste is diapers. Just diapers is like, to me, that was insane.
Adam makes direct. I about 50% of the garbage bags that leave our house are
totally.
Diapers.
I started working at Zymochem before my son was, a twinkle in our eyes. And that first week we brought him home, we literally doubled our garbage output. And I was like, that
little bit of context.
Totally.
If you ever need test cases, just call me. We have an abundance of them.
We actually just had a run with some of our material with a diaper manufacturer where they made a whole bunch of diapers, and we're going to do an in-home use test. That's sort of an industry term for getting diapers on babies and seeing what parents think about them. Sometime within the next month or so, we're trying to get that done. So I think we're going through an agency. I don't know if I could directly give them to you, but
I'm not kidding. But yeah, we have a lot of. Let's just go with my second born. I got a call from daycare last week, and they asked if anyone could bring him clothes because we had a blowout situation. He's a big boy for his age. They're like, we don't have any spare clothes that fit him.
Oh no!
So my husband happened to be off because the holidays ran clothes into daycare. But yes, Gus was running around with no pants on.
Diapers are a big topic.
Diapers are the only topic at home.
Yeah.
Do we have them? How many do we have? Did everything stay in them?
Totally. No,
yeah.
I get that. We are literally just on the tail end of potty training. So my son is almost out of diapers except for the overnight pull-up, which...
It's a really great place to be, man.
Yeah, it is.
So traditionally, the supply chain for everything from diapers to plastics to cosmetics, and you mentioned this too, but I went down an AI rabbit hole about a year ago, and it's almost impossible to find a consumer product that is not petroleum based in some form.
Yeah.
You know, whether the additives or just the plastics, and we use plastics here, and we all interact with plastics in our daily life. But so you guys are trying to create an alternative to the petroleum based supply chain, and the benefits of that are not only in the manufacturing process, which uses a lot less energy to produce the raw material, but is your output a chemical, or is your output the actual material itself?
So it depends.
Okay.
Zymochem is sort of bifurcated in some regards. We have this super absorbent polymer that I just talked about, and I could talk a little bit more about like exactly how it's made. Maybe not exactly, but like some of the overall
broad
steps.
strokes.
Yeah, for the actual material. So we're making the actual super absorbent polymer, and we are also looking to make our own Zymochem branded diaper at some point in the future. And so we're looking to some different diaper manufacturers to see like if they'd be willing to work with us, because not just the super absorbent polymer itself, but the entire diaper is made out of plastic. There may be some diapers out there that have like cotton or some wood pulp fluff, but for the most part, the back sheet, the waterproof parts, that's all plastic. And we want to make the world's first fully compostable diaper. And so that's something that we're working towards. The other side of the company is making chemicals themselves that can be used to make, for instance, nylons. Zymochem has a partnership with Lululemon. We also have a partnership with Toyota Ventures, and we're working with them and a few others to sort of develop chemicals that are traditionally made with petroleum, but make them with bio-based materials. And so, for instance, Lululemon has been working with us to develop some bio-based nylons, and the chemical that is used to make bio-based nylons can be made with microbes, and we have developed a microorganism. We call it our C2 or C squared. That's carbon conserving microbes. So if you think about the way that we breathe in oxygen, we breathe out CO2. What's going on there is we're eating, I don't know, Christmas cookies, and we digest that. But really, on a cellular level, that sugar in that cookie is being broken down through our metabolic processes. It's being combined with that oxygen, and we're breathing out the CO2 from that process. It's the same with E. coli. It's the same with elephants. They eat a sugar. They, for the most part, use oxygen and convert that sugar into CO2 and extract the energy from that chemical conversion. Our scientists have developed a system to do that without releasing CO2. So all of the carbon that comes in as sugar is going either into make more cells or to make the chemical that we're interested in making. And that has a lot of benefits. Obviously, there's CO2, atmospheric warming, climate change, all of that. That is like one of our key drivers. But the other sort of business aspect of that is when you're feeding, let's say, 100 grams of sugar and they're converting 50% of that to CO2, that's 50% of product that you're not making. So there are cost savings in having all of the carbon that you're feeding going into making the product you need. And so it's a really efficient process.
So petroleum supply chains, you're pulling carbon-based materials from deep underground.
Right.
You're processing them through a very energy-intensive manufacturing process, and then you're releasing them into the atmosphere.
Yeah.
In this case, you're using biology to do a lot of the processing for you.
Yes.
So it's more efficient at scale. I know you guys still have to scale up, but it's more efficient at scale, but also traps the carbon, and it becomes usable as opposed to releasing it in the atmosphere.
Yeah. So the petroleum-based process is pretty complex. They're not...
And it's been built over hundreds of years.
Yeah,
100 years.
We often talk about, at least on the superabsorbent side of things, they've been making superabsorbent polymers from oil for 50 plus years, and we're trying to catch up in just a handful of years. And so these things take time. But the petroleum-based process, they're not just, they're not pulling out nylon from petroleum. They're pulling out crude oil or whatever, and they're fractioning it into different segments, and some of it goes to diesel, and some goes to gasoline, and some goes to some of the components that go into plastics and other things, and some of it goes to make specific chemicals for other whatever. And so as we think of like a life cycle analysis, the amount of energy and water and waste products and everything like that go in and come out, they're able to kind of fraction that off because, I don't know, a kilogram of oil can be split into 100 or 1,000 different things. And they can say like all of the carbon credits or whatever you want to call it, they go specifically to the petroleum or the gasoline or whatever. And then the byproducts for them are used to make all of these other chemicals and things like that. So they can say like, man, we're getting into the weeds of things that I don't know too much about. So I don't want to get into there, but specifically like they might not be releasing carbon into the atmosphere when they're making the component that goes into nylons. But when they're pulling oil out of the ground, there are methane emissions because they can't capture everything. And, there are environmental disasters that happen with oil tankers and things like that. And there's obviously the emissions of burning the gasoline. That's like the major use of that oil. Maybe gasoline isn't the major user, but there are externalities that come along with using oil regardless of how it's being used. There are also going to be externalities when we're doing this in a bio-based way. What we're trying to do is say that doing it in a bio-based manner has fewer externalities, and it makes things more sustainable, more reusable, more cyclical, and we think it's really important.
And for a consumer product where between manufacture and use might be 30 days, 60 days, but the product itself will last for 500 years. Like there's a mismatch there.
Yeah, totally. So our goal with that compostable diaper is that, you buy the diaper, you use it how it's used, then it can go into maybe an industrial composter. Out where I live, we have green bins where all of our food waste and yard waste can go there, and it's taken to an industrial compost site. And then you can go get some free compost a couple days a year to use in your yard if you'd like. And in my mind, what I would love is to have a system like that where you can just either toss your used diapers into that type of compost that may be a challenge due to the human waste component, or maybe we have a specific service that can pick up those diapers, and then you're kind of making a compost that can be used to feed the plants that make the sugar that then go into the fermentation that is used to make the actual material, the bio-based material. Exactly, full cycle.
And when you guys do scale up for manufacturing, will the manufacturing process, and I'm sure it'll be different if you're producing a chemical or a raw material versus a finished good like a diaper, but does that start to look like food processing, like that type of industry? I know like brewing beer was one of the similar processes, but what will a manufacturing plant look like?
I think a manufacturing plant will, I've never been into a food manufacturing plant, but I think it'll look like an actual chemical manufacturing plant.
Okay.
Maybe like crossed with a brewery or something like that. So we actually have a guy on our team. He's like a brilliant scientist. He used to work for, I don't remember exactly which company, one of the, plant-based meats, like Impossible Foods or something like that. And he has taken a lot of his knowledge from that realm and applied it to how we convert our biopolymer into our superabsorbent polymer. So maybe I could just talk through the process of making SAP.
Start at the beginning,
yeah. So We have developed a microbe that can eat sugar and make a biopolymer.
What does develop a microbe mean?
We have, so it's not just the microbe itself, but we have genetically engineered it. And one of the first things that I did when I worked, actually this is when I was still working in Tennessee at Oak Ridge National Lab. I was working on a project at the National Lab to develop genetic systems, genetic tools to engineer microbes that are really difficult to work with. If you think about E. coli or like brewer's yeast, things like that, any microbe lab in the world knows how to engineer those microbes. They're really easy. They've been developed over hundreds, maybe 100 years. But there are tons of microbes out there that have very specific skill sets that are challenging to genetically engineer. And our lab was specialized in developing the tools that would allow you to cut out a piece of DNA and put in a different piece of DNA, or even just, we don't like that gene because that gene has the microbe make a byproduct that we don't like. And so we'll just cut those genes out, and then it doesn't make that byproduct anymore. Excuse me. So one of the first things that I did when I was working with Zymochem, Zymochem had won an award, a grant, to work with the national labs to develop their microbe strain, and I happened to be the scientist that helped them out with this project. I developed the system that would allow us to move DNA into the cell so that it could, be used to cut out or replace or all that other stuff I just mentioned. To do that, what we did is essentially we camouflaged the DNA. So microbes have ways of saying that DNA is not my DNA. I'm going to chew it up and get rid of it so that it doesn't infect me. Microbes encounter bacteriophages and all these things that are trying to attack it all the time. Nasty and brutish is their life. So what we did is we basically developed a companion strain of bacteria that would camouflage the DNA. So then we moved it in, our bacteria strain wouldn't just immediately get rid of it, and it would allow us to kind of move in pieces of DNA that we might want to introduce a new way of making our chemicals. So I mentioned the carbon conservation microbes that we produced. That is a microbe that has a several step process that is completely non-existent in nature. We've taken genes from a handful of other microbes and we've combined them into a cyclical pathway to enable them to metabolize things without producing CO2. I feel like I keep getting into the weeds here.
Sorry. Well, it's really interesting hearing you talk about bees.
Yeah.
And then talk about this, because it sounds like a lot of the principles still apply when you talk about how you are specifically selecting genetics, which essentially is DNA when you get down to the nitty gritty of it. You're applying that to make sure you have healthier bees. It sounds like you're doing the same thing.
Totally. Yeah, that's a really good point. When we're engineering microbes, we often include something like, we call them selectable markers. So if you move a piece of DNA into a microbe, how do you know that you are successful? And how do you get that microbe out of all of the other microbes that might not have gotten it?
In a jar with some Dawn dish.
Exactly. So one of the things we might do is include a gene for antibiotic resistance. Or sometimes what you do is you include a gene that causes the microbe to make a specific pigment. And so when you grow it on like a Petri dish, you'll see a little colony and you'll say, oh, that one's blue. That one must have the gene that I'm interested in. And so you pick that one and you keep working with it. So I forget what your original question was.
I think you were talking about the fundamental science at the company.
Right.
Yeah.
So, I'll get back to that. So,
no, this is good. This is great.
Yeah, so we have developed this microbe by genetic engineering techniques. We've knocked out certain genes. We've inserted other certain genes that allow our microbe to have the specific performance that we want. And that's sort of coupled with the process itself. So you have the microbe, but then how you grow the microbe, and those are very tightly connected. When we put our microorganism into a 50,000 liter tank, you can imagine at the top of the tank, the environment might be different from the bottom of the tank, or how you mix it is really important because you need to make sure that any of the sugar you're feeding it or the air you're pumping into it gets to all parts of that tank equally. And so we may need to specifically engineer our microbe to be able to handle the environment of that fermenter. Our biopolymer we're making, it's polyglutamic acid. This is stuff that's known, so we could talk about it. Polyglutamic acid is a really high molecular weight biopolymer. And when our microbe is making a lot of it, it gets really viscous. We literally can fill a mug with it at the end of a fermentation and hold it upside down, and it won't flow out. And so you can imagine mixing a tank with, peanut butter in it at, 100,000 liters. That's a big engineering challenge. So we have, the formulation of our growth media, we have the microbe, and we have our process, and we're constantly thinking about that interplay. And that's just for the fermentation to get the microbe to make what we want it to make and not make other things.
Do you have scientists and engineers working side by side?
Absolutely.
Okay.
Yeah,
So there's the fundamental science, and then you have, it's really process engineering.
Yep.
And your inputs are microbe, sugar, air, or what are the main main ingredients at that level?
Yeah, so we have what's called a defined media. So that means that every single chemical in our growth media we know. If you think about brewing beer, for instance, a lot of times you have like your wort is just like wheat that has been sort of milled, and then I'm forgetting all the steps, but essentially that is what we would consider a complex media. You don't really know all of the chemical components of that wort. You know that it came from wheat, but you don't know that there's 5 grams per liter of glucose or 6 grams per liter of whatever. We know the precise concentration of every single chemical in our growth media. The major component is the sugar we feed. Beyond that, there are, you need a way to buffer it. So polyglutamic acid is an acid. It will lower the pH as you ferment. So we need something in there to stabilize that. There are certain trace elements you need. So some enzymes require like a specific metal, like nickel or cobalt or things like that, magnesium. So there are things like that in our growth media. Salts, everything needs salts. There are microbes have specific, membrane embedded transporters that require, sodium or potassium or protons, things like that.
And the output of that process is a chemical compound, not a material.
Exactly. Yeah. So at the end of our fermentation, we have a really thick, viscous broth that has our polyglutamic acid. It has our microbes in it. It has any sort of byproducts that our microbe might have made, and then all of the residual chemical components that I just mentioned.
Yep.
And so we then have a process to purify our PGA. And that is also a very complex, complicated process. We use things like filtration and centrifugation to remove the microbes and impurities. But you can, again, imagine trying to filter peanut butter or trying to filter honey. It's a challenge.
It's a pressure.
Yeah. So,
are the microbes still viable after, or is it kind of a one and done situation?
I'm not sure that I can talk about that.
Okay, never mind. Done.
We found the line.
Yeah.
Found the line.
Dang, that's your job, not mine.
So I will say at the end of the fermentation, the microbes are still alive.
Okay.
We then sort of through our processing, they may or may not be alive, but we're trying to remove all of the microbes at the end.
For sure.
So, yeah.
And have you, as far as large scale manufacturing, it sounds like this is still at the batch run or like prototyping level in some regards?
So we've done some pilot scale runs.
Yep.
We're in the process of setting up a pilot scale facility in San Leandro, where our headquarters is. But we also have scaled up to, I think 45,000 liters is the highest, largest scale fermenter that we've run in.
Is that per batch or per run?
Per batch.
Per batch.
Yep.
Okay.
Yep. I don't know if I can share yields and things
Well,
like that. I probably
that's right.
shouldn't, but
Yeah.
we've done some really large scale
Yep.
fermentations and in the sort of associated downstream purification processes, and then we haven't even gotten into the chemical conversion step yet. But our goal is much bigger. So we're looking in the next year to produce hundreds of metric tons of our superabsorbent polymer.
Awesome.
And yeah, it's going to be a challenge, but it's going to be a great challenge, and I think we're really well set up to do it.
And your team is working alongside your engineers are working alongside your scientists at this scale. From a large scale chemical manufacturing, are there outside engineering firms that you guys would work with on scaling up? I know, like when we're building our paint line right now, it was really a combination of our engineering team plus other subject matter experts, whether it was on a chemical wash system or the conveyor equipment or the powder application. It really turned into a mix of outside skill sets and inside skill sets. But is it similar, do you think, as you guys scale up?
Yeah, so there are specific pieces of knowledge that our team has
Yes.
that is like critical to our process. But as we scale up and as we think about building, a kiloton plant or a multi-kiloton plant, our eventual goal is to have a US based facility that can do end to end and a few more ends beyond that. But essentially, the fermentation, the purification, the chemical conversion, all the way through to the final superabsorbent polymer, we want to have that in one location. That cuts down on costs and it cuts down on carbon
awesome.
emissions. But to build a plant like that, there's some really specialized knowledge you need. And so we do have some really great consultants we work with, and we have talked with some engineering firms that have experience building these types of manufacturing facilities.
And that super absorbent polymer raw material, the next step is a diaper or some type of component.
Mm-hmm.
Is that a molding process, or how does it get formed into the final shape? I know we talked a little bit earlier in the week about injection molding, and there's other, you have some plastic manufacturing where it comes as a sheet and then it gets, formed around a die, or what does that next step look like?
Yeah, so we're here again is you can develop something at the bench or in a pilot scale facility. That isn't going to work at manufacturing scale. So we're sort of in this mode of prototyping a few different systems for doing that. But essentially, we're in a place now that we have a really good process that we think we can scale to kilotons annually. So our PGA is combined with a chemical that PGA itself is soluble in water. That means it's dissolved in water. And if you had a dried PGA solution and you dumped water onto it, it turns into a goopy, slippery, sticky mess. And nobody wants that in a diaper or in other applications. And so what we do is I think of PGA sometimes as like a bowl of spaghetti. You got a bunch of different strands in there. And if you're boiling a pot of spaghetti, they're all kind of swirling around and not necessarily connected to each other. But then we do a chemical conversion process that sort of cross-links those noodles together. And so then when you have some of this dried superabsorbent polymer and you put water on them, they swell up and not go into solution. They're not soluble. And so our process is taking our PGA, adding this chemical component, and there are some very specific ways in which we have to sort of mix it and blend it and make sure it's dried, and things have to be added in a very precise ratio. But essentially at the end of all of this, depending on the particular process we choose, we will have a dried super absorbent polymer that will then have to be milled into a specific granule size.
So then is it similar to injection molding, where you have like injection molding, you have little plastic BBs that get heated up and then liquefied, and they get pushed under high pressure into a die or into a mold. But your raw material that, say, a manufacturer, a component manufacturing company would get once it's dried, what will that raw material look like? And maybe you can't go into detail on this, but I'm just trying to like see parallels to other polymer or plastic manufacturing.
Sure. And honestly, we had a few engineers on our team that came from that world as well. And perfect. So we're using some of, their knowledge base, but it is a little bit different. I think for injection molding, as you just mentioned, it sort of starts out as a granule and then is sort of extruded or converted into some sort of sheet or whatever shape you need. Here, the end product is the granule. So when it goes into a diaper, there's, I don't know if you've held a diaper recently, but if you kind of squeeze it, you can sort of feel little granules in there.
If you've ever accidentally put one through the wash machine, which I don't recommend, it's when you said that like goo, that's what it turns into. Really? It's like, I'll bring you a diaper, you can cut it open.
Do your kids ever play with I think they're called like Zorbies or Sorbies or something like
like
these
the water beads? Yeah.
Oh, okay.
That's sort of how I think of it, but on a really small scale.
I see.
So they're, we're talking a few hundred micrometer scale. So not quite a powder. Powder is super fine. So we kind of refer to it as a granule. The granule then can swell up to maybe like a millimeter or something, a couple millimeters across.
Yep.
So in diapers in particular, we're looking at a very limited range of particle size distribution, because if it's too big, then the baby can feel it when it's sitting on it. If it's too small, it might sort of sift through the the core material. It's mixed with like a fluff pulp, and there's like the top sheet that the baby sits on and the back sheet. If it's too small, it might come through that. So
the manufacturer, the finished goods manufacturer, probably has their existing tooling and manufacturing process, and they're more or less using your input into their existing manufacturing process, potentially.
For the diaper manufacturer?
Yeah. Yep.
Yeah. So these are tests that we've been running this year, actually.
Yep.
Do we have a drop-in solution?
Cool.
Can we just say, turn off the petro-based SAP, put in our SAP, and it just keeps running the same? And so we've had a lot of success.
Your commercialization channel is already there. It's just having an equivalent to drop in.
Exactly.
Yep.
Yeah, and we have, been in conversations with a bunch of diaper manufacturers and basically saying, our material's great, please try it out. And we've had some success in those conversations, and we've had some line trials where we've been able to convince them to turn off their Petro SAP, turn on our Bio SAP, and they produced a bunch of diapers for us, and we're hoping to get those diapers tested on some little babies sometime in the next couple months here. So
that's awesome.
How long does that process take? Like, I think that's what's really like, how long from when someone, it could have been someone before you, started working on that microbe to create the different DNA and change its genetics to now you're running diapers at a major manufacturer? I think people lack context for some of that sometimes.
So
ballpark. Sorry, you don't have to get into the
no.
But you know what I mean?
I've been working with Zymochem, working with them for 6 or 7 years.
Okay.
I've been working for them for just over 5. So when I was a postdoc at Oak Ridge National Lab, I was working with them on that project. Postdocs at national labs tend to be fairly short. So when that appointment ended, Zymochem needed somebody to do what I was already doing, and I was able to kind of make that transition and go work for them. So I don't know when the inception, like the thought inception happened, but I think I joined pretty early in the process. So there's an initial screen of microbes to figure out which one makes the best or the most amount of PGA. That happened shortly before I started working on the project. And so I would say 6 or 7 years.
Okay.
Yeah. Basically the duration of my time with Zymochem is how long we've been working on it.
Cool. I mean, we talk about like powder coat line and doing things like that, and how that process being a couple years seems super long, and then you start to look at, creating microbes to create SAPs.
Yeah,
and
totally. Yeah,
lots of acronyms.
I started working at Zymochem in 250 milliliters, just tiny little flasks. And then shortly after that, we were working in 2-liter bioreactors. And then we started working with another national lab out by me. Lawrence Berkeley National Lab has this facility called the ABPDU, and more acronyms. I can't remember. It's like the Advanced Bioprocess Development Unit. I missed some words there. But they have a 300-liter reactor. And so it's sort of step by step. And while we're developing that formulation for the growth media and the process of doing that fermentation, we're also developing the microbes. So we might notice like, wow, when we grow in this 300-liter fermenter, it's making a ton of acetic acid. Maybe I shouldn't say the specific byproduct. It's making a ton of a byproduct. So we should go back and knock that out. And when you knock that out, we have to go all the way back down to, a shake flask. How does that impact the growth? How does it impact the production rate of PGA? And so there's sort of this back and forth process for years. And then we settle on a strain that we like. We settle on the formulation and the process we like. And then we've just, over the past 2-ish years, we've been working with a contract manufacturing organization that has 45,000-liter tanks and 10,000-liter tanks. And we sort of, again, stepwise increase. And we're sort of at a stage now where we've locked in the microbe. We've had to iterate on the growth media, the formulation that we use. And now it's sort of figuring out how fast do we need to mix it, or how much air do we need to add, things like that as we go up in scale. Those things are expensive, so we can only do so much at a time. But yeah.
Well, I know you gotta run, but before we end, I know I got to give my Wisconsin pitch here. Wisconsin's a big manufacturing state. As I mentioned, there's tons of food processing, but I know there's some chemical manufacturing as well. But when you guys go to build your big plant, maybe you should look at Wisconsin.
Totally. No, I wanted to speak to that to some extent. Maybe not the manufacturing, but just my Wisconsin roots.
Please do.
I was reading the document you sent me this morning about like sort of the ethos of this podcast and things, and it had me reflect upon my past and what got me to where I am. And at first I was going to start at college. I went to UW-Madison. But I think really it goes back to childhood for me. My dad owned a construction company when I was growing up. I basically grew up on a construction site. I lived in a house that my dad built, that I helped my dad build, here and there as a kid, whatever you can do then. One of the first things I remember doing is holding the string line for my dad.
I think we've all done that.
Yep.
I just speak for yourself. I wasn't allowed to help with
that.
Your
dad had a concrete.
Yeah, that was a little too precise. Okay. I wasn't that kid. Yeah, so I wasn't allowed.
my dad's company was M&S Construction. They were largely concrete construction. So I spent every summer in high school and a lot in middle school wheeling wheelbarrows full of concrete up. Yeah, so I'm very familiar, and I think I just knowing that you can do a thing, knowing that you can build a thing, seeing people actually build a house or actually pour concrete or whatever, like,
or even if you don't have all the information right away, like get started, figure it out, like
just having the appreciation for that. So many people don't think about that, like, oh, there's a house. No, not everyone looks at it and thinks yes.
I remember a conversation you and I had years and years ago about, we were both in college and we were studying whatever we were studying and thinking, we're hot shit smart guys.
Yeah.
But we had a conversation about there's different kinds of intelligence.
For sure.
There are guys that can build a house. There are guys that can rebuild an engine that never went to college.
No.
They know more than any of us would ever know about that sort of stuff. And it's important to acknowledge that. And as I just mentioned, growing up in a household where my dad not only built that house, but he built other things in that house and around that house. That sort of instilled in me this nature of making. And we talked about beekeeping, and I have a ton of hobbies, and I was thinking about sort of what is the theme of my hobbies. It's about making things and growing things. And I think it goes all the way back to these sort of roots of knowing that you can do a thing. And if you don't know right away, you can look it up, or you can ask somebody how to do it. And, there's value to the apprenticeship model to learn how you do a thing. My first job out of college, I worked for an engineering company called RMT. It was in the smart burn division, and essentially what they did was look at coal burning power plants and figure out how they can reroute the airflow in those coal burning power plants to help reduce emissions. So at the time, there's nitric oxides and things like that sort of lead to acid rain, and they were able to kind of use some complex computer modeling to figure out airflows and figure out how you might reroute the air. Anyway, I was working in a power plant with some older guys, and I don't remember exactly what we were working on, but it was essentially I needed to hold a thing, and we were doing a multi-step process, and I just intuited I needed to go over there and hold the thing for the next step, and I did it, and the guy looked up at me and was like, "Oh, you know how to work." And I was like, that to me,
it's such a common theme.
Yeah, it meant a lot to me.
crazy.
Like it was like the biggest compliment to me that like
you've seen the full scale. You've seen things getting built at the end use level in construction, and then you see the microscopic level.
Mm-hmm.
And you even mentioned your current role. You're kind of working with the technical people and people that aren't quite as technical in translating different things and putting it in languages that everybody can understand. And we see the same thing here. Like, you need those people that can speak, they're not fluent in every language, but they can speak enough to help communication. And I'm sure it's like the guys on the floor always appreciate the engineers that will roll up their sleeves and get their hands dirty. And I think that is a very Wisconsin thing.
Yeah.
Which is cool.
Yeah, for sure. I've lived in a handful of states and throughout my career and educational path, and I encounter people from Wisconsin all over the place. And one of the co-founders for Zymochem is a UW-Madison alum from
That's
Wisconsin.
Cool.
Yeah. And there's just sort of, there's like a familiarity. You kind of speak a little bit of the same language.
It's funny you say that, because part of the reason we named Wisconsin Lighting Lab came from Tyler living in Boulder for a few years. And I remember him saying, the Wisconsin people always found each other.
Yeah.
And they were very proud to be
They'll
from
always
the
tell you you're
Midwest.
from Wisconsin.
Yeah, it was
There's no doubt.
He said it was just this thing, you're another Wisconsin person.
Yeah.
It was, and that was, back when we were naming the company, it's only a couple % of our business is in state, but there's something about that brand, that Midwest brand, those Midwest values that does translate.
Yeah.
It's way less about the sales piece of the business, and it's way more about the operations side.
Yeah.
It says something about that piece of it. It's less about where we're selling the product and where it's being installed, but more about who
That's a
we
good point.
are.
Yeah.
Yeah.
It says something about us as people and what
Yep.
that means. It means something to us that we're from Wisconsin.
Absolutely.
For sure.
Well, thanks, man. This is one of my favorite ones.
This is
I
so
appreciate
cool.
it.
I'm giddy over here.
I appreciate on short notice you doing this, and you've got just a wide range of knowledge to share. And maybe next year when you guys are back, we'll have to do round 2.
Yeah, for sure. I feel like I only scratched the surface, and
There's a lot there.
I do want to say it. I love what you guys are doing here.
Yeah.
I love
Thanks for reaching
that
out.
you've, when you go off to college and there's sort of this mindset that I got out.
Yeah.
I don't need to think about my hometown anymore or
Yeah.
whatever. I love that you've brought manufacturing back to Fond du Lac.
Yeah.
I'm getting teary.
Oh, man. Well, thank you
it
very much.
means a lot. Yeah.
Thank you very much, man. Appreciate it.
Of course.
Yeah.
A couple years ago, so I'm part of the Alameda County Beekeepers Association.
Nice.
That's amazing. I love it.
So Alameda County is one of the biggest counties in California, in
Okay.
the U.S. actually, by population. It has Oakland, Berkeley, where I live,
Yeah.
all the way out to Livermore, where Naomi works. That's where the Lawrence Livermore National Lab is.
Nice.
And so I just got elected as the VP of that club.
That's awesome.
But they have a community garden plot where they're trying to put pollinator, like friendly plants in there, like a big diversity of plants. And they also have a couple hives there that they use for educational purposes. And, sorry, to get back around to that picture, there was a club member who donated a bunch of, I think they may have been native sunflowers. And there were way too many, so I took a few home and put them in my yard. And for the last couple of years, I've been picking my favorite sunflower and taking the seeds from that and then planting those ones. And so this year I had a big patch of sunflowers. And it was like golden hour, you know, just before sunset. I went out and there were just bees all over them. So I snapped a bunch of pictures. Cool. And I got that one of a bee just about to land, and it has those big pollen baskets on its legs. And I thought that's perfect for a label for my honey jars. And
my neighbor's a science teacher in Milwaukee, and he's trying to get like the bees to return. So he planted a bunch of sunflowers, and he does a lot of just planting in general around his house, and it's been cool talking to him about it. But yeah, it's a whole world that, unless you're focused on it, it just kind of happens without without you knowing.
Yeah, totally. One of the things that they tell you to do as a beekeeper is have a water source for them, like something that bees can go to and hydrate, because they use water as evaporative cooling, and then also when they eat their own honey, they need to dilute it a little bit.
Yep.
So they need actually a good amount of water.
So is honey diluted, or
no? Honey
this is the
concentrated nectar.
Okay.
So they actually have a separate honey gut. They'll go out and drink a bunch of nectar, and they'll bring it back to the hive, and they actually have like little filters in that honey gut that will like pollen and stuff like that, and they'll kind of, I don't know if regurgitate makes it sound gross, but it's like they'll like.
I heard it described as bee vomit.
Sort of, but bees are like a really hygienic, clean animal, and so I can't remember exactly if they sort of daisy chain sort of past the nectar bee to bee up to where they store the honey, or if they just sort of the forager passes it to one bee and then that bee takes it up to where they store it. But they'll process it, they evaporate it by flapping their wings and getting airflow in there, and then it concentrates it. There's also an enzymatic process that inverts the sugar. So I'm forgetting, I think so sucrose is glucose plus fructose in equal amounts. They're kind of joined together. And they'll split a portion of that into glucose and fructose. And I think if fructose is higher, it allows it to get super concentrated without crystallizing. And that's essentially what it does, is it's super concentrated sugar with all of the other like things that come with, you know, nectar, like the antioxidants and things like that.
So is honey just a byproduct of things they're already doing in the environment, or what is the reason they're making?
They specifically store it to make it through winter. Yeah, and
so it's a high calorie.
Yeah,
they eat it.
Yeah, they eat it.
Okay,
that's how they power their flight. It's sugar is high energy, and they also collect pollen, and that's all protein, and so that's how so you have your carb and your protein.
Man, that's cool.
And they need a diverse pollen source to get. Same as we need diverse, you know, amino acids and essential amino acids and things like that from different things we eat.
And then we take their excess.
Yeah.
We take their inventory.
Yeah. We give them shelter. We take care of them. We treat their diseases.
Yeah.
We give them a place to live, and we collect rent at the end of the year.